All right, how's everything going?
Good.
Did everybody notice that there's a quiz online?
Yes.
We did not notice that there was no password that we could have started on it.
There's what?
I figured you were gonna post a password, but it was just open.
No.
So some of us were just waiting.
Nope, you can spend 24 hours on it if you want. But probably not. So no questions from last time?
Do you want us to take the quiz right now, or?
No, you can do it anytime you want.
Okay,
It's
good.
open until 8 tomorrow morning.
Okay, good.
Yeah. Am I what? I might stick with quizzes this week. I haven't decided.
Yeah, but what about SLP? Like, what do you want? What do you want?
Yeah, that's coming up, isn't it?
Yeah.
When's that due?
Six.
6th?
What's that?
So I'm thinking Monday. So what do we want for an SLP? Is that really a Bills hat?
Yeah.
We talked about this before, I think.
Have we?
Yeah, I was a Bills fan for a while.
Oh, really?
Yeah, I came from New York, so.
Oh, I was born there.
Oh, okay. Cool. So SLP, for winter term, your deliverable is a poster. So there's a template that you can download and fill in, and then cut off the page of instructions at the bottom and just submit that by the due date as a PDF. And then we'll print it out. And I believe the plan is to do that expo again, this time in the digital lab and the room down on the corner. But I think we're also going to videotape presentations from each student. We're going to go around with the camera and just have you like 5 minutes, tell us about your project, what you're working on, how far you got, if you have something to show and tell, that kind of thing. And we're going to make those available on the ENGRCS website. So your only deliverable per se is that poster, and then to show up for the presentations.
Okay.
And then in spring, your deliverable is actually a formal written report that summarizes everything you've done on your project, and there's a whole detailed template for that.
If you change, if you change like a little thing up, is it okay? Just like add it onto the.
Yeah, if you made tweaks to it, that's normal,
Yeah.
right? Because you're figuring out what you want to do and what's practical and what's feasible and what's interesting. So things will definitely shift around somewhat.
Okay.
If you totally change gears, right, I was going to make a video game, but now I'm inventing a dot matrix toaster, then tell me about that as soon as you decide, and we'll talk about it, and as long as that's appropriate.
Like dot matrix toaster.
They make dot matrix toasters, they're really cool.
So it just burns the part of the toast that you want to write on.
Yeah,
So you either got bread or burnt toast.
yeah. Doesn't have to be burnt, you could brown it, I guess. But you'd have squishy sections in the middle, which would be a little weird.
Or it could like toast the whole bread and then
And then
over
straight.
toast the.
Oh, yeah, that too. All right, other questions? Dot matrix toaster is a great SLP.
Let's see if we can like 3D print the butter and jam.
Yeah.
Like have a checkerboard pattern.
Mm-hmm. All right, so let's talk about dynamic programming. So let's start with Fibonacci's. All right, so we have a Fibonacci sequence, and we call these F1, F2, F3, and so on, and the secret here is Fn equals the sum of the two prior terms. So the nth Fibonacci number, just calculate the two Fibonacci numbers right before and add them together. And we touch on this in discrete structures 215. It's tied into rabbit populations, it's tied into the things, the patterns you find in sunflowers and pine cones and stuff like that. And it's filled with all kinds of rich symmetries. 8 times 21 is 168, 13 squared is 169. Each of these, if you square it, it's the product of the two numbers on either side, plus or minus 1. And it alternates plus 1, minus 1. And it's got all kinds of crazy stuff you can find in there. So it's studied and used for lots of things. So if we want to write some code to calculate Fibonacci numbers, it's not too bad to do by counting up, right? You just need to keep track of your last two numbers. Add those together, that becomes your third number. Throw away your first one, just remember those last two, add them. That's your fourth number, throw away the second one, that's your 2, and so on. But we can also write it using this definition. This is a recursive definition. And we can say the nth Fibonacci number is just the sum of the two prior Fibonacci numbers. So here's some code to do that. This will happily seg fault if you run it without an argument. So it's a bad example of code. But if you give it an argument, it scans it into n, and then I just call my Fibonacci function fib. That's the value n. And my fib function basically just takes the two previous values of n, calculates their Fibonacci numbers, adds them together, and returns that. So a straight translation of this formula. And if you run this, it seg faults. So why is this seg faulting? And it's nothing to do with the scanf. Because it goes forever. How's it going to calculate fib 5? First thing it's going to do is calculate fib 4. And when I get into fib 4, first thing it's going to do is call fib 3. And that'll call fib 2, fib 1, fib 0, fib minus 1, fib minus 2, and so on. And it never comes out of that.
You don't want to have n less than 0, or in this case, n less than 2?
Yeah. So let's throw some diagnostics in here. So let's print out a message each time that we enter this routine. And then let's put out a message when we leave.
What's the VI command for copy line and paste line and all that?
So big Y will copy, and then the little p will put or paste.
Interesting, one line at a time?
Yeah, but I can also say like 5 copy, and then paste those.
Thank you.
Yeah. Q exclamation mark. Ignores your changes. So if I run this on fib 5, right, you can see the infinite descent going on. And that tells you right away, oh, I forgot something. So it goes as deep as it can, and then the stack blows up. So let's put a test case in here.
design, they call that a bad Z collision, where it's like you jump off a cliff and then you don't land on the ground, so you
Nice.
keep falling right through the ground.
Cool.
Miss the zeros somewhere.
I like that. A bad Z collision? Makes sense.
Z-axis.
Yeah. All right, so when I first come into fib, if n's less than or equal to 2, I'm just going to return a value of 1. Otherwise, I'll do this recursive thing. So this will give us correct values. So fib 5 is 5, 1, 2, 3, 5. Fib 6 is 8. Fib 7 is 13. Fib 8 is 21. Fib 10 is 55. But to calculate the 10th Fibonacci number, I had to do all of this. And on, and on, and on, and on, and on. So what happens, we try to calculate fib 10, we know we need the 9th Fibonacci number, which needs the 8th, 7th, 6th, 5th, all the way down to the 2nd. The 2nd comes back right away. We need the 1st Fibonacci, that comes back right away. That gives us Fibonacci number 3. And then we go right back in and we start calculating Fibonacci number 2 again. And we do this over and over and over again. So let's put this into let's just see how many times we're entering our Fibonacci code, and it's 109 times. And if we try to calculate the 20th Fibonacci number, we do that 13,000 times. And if we want the 30th Fibonacci number, we do that 1.6 million times. Yeah.
Start reading that one quite well.
Could have been that delay on the projector. So when we calculate the 30th Fibonacci number, the number of times that we calculate fib 28 is 2. Because to calculate fib 30, we need fib 29 and fib 28. To calculate fib 29, we need 28 and 27. And so on. So we only call fib 28 2 times, but the number of times we calculate fib 27 is 3. Fib 26 is 5. Anybody want to guess what fib 24 is?
I'm missing what we're looking at here.
So looking at the number of times that we called fib 24 or fib 26.
Oh.
Let's skip 25. So we called fib 28 twice, we called fib 27 3 times, fib 26 5 times, fib 25 8 times, fib 24 13 times. What's fib 23? How many times do we call that?
That would be 21.
21 times. So the number of times that we end up recursively calling the nth Fibonacci number is itself described by a Fibonacci sequence. That's kind of the nature of Fibonacci numbers. They just pop up all over the place. And Fibonacci numbers grow geometrically, in a sense, right? They're the sum of the two previous ones, so it's not quite doubling, but it's kind of like doubling, which is why fib 20 takes us a total of 13,000, and fib 30 takes us 1.6 million. And if we do fib 40, it never comes back. It'll run probably for the whole class.
This is just an inefficient way of calculating Fibonacci?
Mm-hmm. It's a very inefficient way of calculating Fibonacci because of this. So let's go back to Fib 30. How many times did we ask to calculate Fib of 3? 317,000 times. And to calculate the third Fibonacci number involves calling Fib 2 and Fib 1. And Fib 2 and Fib 1 just return 1. So we're making 317,000 calls to a routine that makes 2 calls to itself. So right there we've got over 500,000 function calls. Recalculating the same number again and again and again and again and again. What if I just told that Fib 3 is equal to 2? So,
Could you like create a list or a tree to store all that?
there's an idea.
I'd only calculate if it wasn't already there.
So yeah, if n equals 3, let's just return 2, not 3. Now Fib 30 went from 1.6 million down to about 1 million. Just by hardwiring this value.
Just hardwire and 100 of them, you'll be set.
So if we hardwired another 100 of them, we'd be set. This would take 30 calls, right? So this is what the essence of dynamic programming is. We don't want to hardwire our solution because that's cheating. But the first time we calculate F3, we're going to basically hardwire it. We're going to save it in an array. And the next time we ask to calculate F3, we're going to check this array and say, hey, have we already stored the value of F3? And if we have, we're just going to read it out of the array. We're not going to do any recursion. And we'll do that for F3, F4, F5, all the way up through however many Fibonacci numbers we calculate. So the essence of dynamic programming is the following. Initialize a save array. There's probably a better word for that, but we're going to call it a save array. When asked to calculate Fibonacci n, see if this is saved. If it is, just return the saved value. If it's not, calculate fib n minus 1 plus fib n minus 2. Save that result, and then return. Start with a save array, initialize it to something that tells you there's no value stored in there. Each time we call fib, we'll check this array and see if our number is already calculated. If it is, we just read it from the array and we're done. If it's not, then we go ahead and we call fib n minus 1, fib n minus 2, add them together. And before we return, we save that result into our array. So that's there the next time somebody wants this value. Mm-hmm.
How big of an array do you need to declare? Do you just do an array of size whatever you put in the argument?
If we're using an array, yeah, you can just initialize it based on the argument.
At least in this case.
So you could malloc it, or you can just, if you know you're never going to use more than 1,000, you can just make a static array. Or you can use some other data structure. It doesn't have to be an array. Basically, we need a way to associate some stored value with an argument n.
How quick does this blow up beyond the capability of an int? Like 4 bytes?
Fibonacci's? Oh, I don't know.
I'm willing to bet you don't get past 100. Or maybe 50.
I don't think they blow up that quickly. So fib 30 is only 832,000.
And how big a number can you represent with the, and I can't remember,
2 billion.
2 million, so.
So it'll get there, but I think we get close to 100 maybe. We can find out.
Okay, anyway.
Because we can put dynamic programming into our Fibonacci code and actually make this thing work. So let's do that. So we'll make a save array.
It'll just start spitting garbage if we
Yeah,
call
it'll
it
go negative.
Yeah.
So we'll make an array to save our calculations. So I'm doing this sort of the easy way. I'm just setting my values to 0 to say there's nothing stored there. Because I know that a Fibonacci number is never going to be 0. But the more proper way to do this would be to use a structure and have a field in there that's a flag that says is this element stored or not. And clear those to false and then set them to true. But we're going to do the quicker and dirtier route. So we're just going to have a save array. So we're going to enter fib, and here's what we're going to do. Alright, so we're going to check the element n of our save array. If it's not 0, we know we've already calculated that Fibonacci number. So I'll print my message saying that we're leaving, and we'll just return save bracket n. So that's one change I make to my routine to add dynamic programming. In the very beginning, I check to see if we've already calculated this value. And if we have, then we just return the same value as a function array. Otherwise, we need to actually do some sort of calculation. Find the Fibonacci value. So here's my base case. If n is less than or equal to 2, I'm just going to return a 1. I'm going to get rid of this. Otherwise, set my result equal to the sum of the 2 previous Fibonacci numbers. And before I leave, I'm going to save that result. And now print out a message saying I'm leaving, and I'll return the result. And that's really all I got to do. 2 changes plus declaration of an array. So check the array on the way in. If it hasn't been set, do your calculation, save the value on the way out. So with that change, gotta use the right name for your array. With that change, fib 40 comes back pretty quickly.
So that's already 100 million.
Yeah, it's pretty
You
big.
think we'd get there by 50?
Possibly. Let's find out. So here's the work we did to calculate fib 40. We needed to calculate fib 39, 38, 37, and so on, all the way down to fib 1. So to calculate fib 2, that was hardwired, so we came back right away. We had to calculate fib 1 to find fib 3. That was hardwired, so it came back right away. And then we needed to calculate fib 4. So we entered fib 4 up here. We did a bunch of work. We eventually calculated fib 4. then fib 3 came back right away. And the next time we needed fib 4, we entered and came back right away without any recursive calls. Now to calculate fib 5, we still needed fib 4 and fib 3, so, but it already had fib 3. Sorry, here was fib 5 and here was fib 4, that gave us fib 6. So fib 6 was everything from here down to here. Right, that's the expensive recursion, modestly expensive recursion. But later on, when we need to calculate fib 6, it does it without recursion at all. And if we look at how many times it called itself, 77. It's not too bad. Let's see, fib 45 is pretty close to the bound, so 46 might go negative, if not 47. And it's still giving us the right value, it's just doing it modulo 2 to the 31st. Useful. And for 47, 91 calls. So this is a huge speed up. One term for this is pruning, right? If you think about this tree, already deleted. Right, and this goes on and on and on into your however many nodes, right? In some sense, once we've called F7 here and we've calculated the value, the next time we have to calculate fib 7, we're not going to do any of this recursion, so all the stuff under there gets taken out of our recursion tree, and all the stuff over here gets taken out, and all the stuff over, well, I said for the 7s. But we've also calculated fib 8, and so having done that, actually the entire right side of the tree gets pruned away. And we never have to do this F7, we've done F6 here. And so our recursion tree ends up looking like this. And so we've gone from something that was growing geometrically, like 2 to the n, down to just something that's order n. And for big n's, that's a huge saving. Right, n of 30 is the difference between a few billion and 30. So we can use dynamic programming to speed up lots of problems that have this sort of natural recursive structure. So let's see, which one shall we go with? Let's just talk about the knapsack problem. Any questions on this so far? So, series of problems called knapsack problems. And here's the general setup. You are the millionth customer at Office Max, or whatever your favorite store is. And as a reward, they offer you a shopping spree. right? So here's the setup. They give you a bag, and this bag can hold 20 pounds worth of stuff. And they say you can take as much of anything that you want from the store, the warehouse, etc., as long as it fits in your 20-pound bag. Okay? It's a magic bag. It's really big, but it's weight limited. So you're basically allowed to pick 20 pounds worth of stuff, which you're going to go home and sell on eBay. And so your goal is, how can I maximize the value of the things that I put into my bag? And you got to think about it. You can't just grab the shiny stuff first. If you were to grab a bunch of external hard drives, those things are heavy, right? You might get 5 or 6 of those, and they might be worth $100 each.
External solid state drive.
External solid state drives will be lighter and worth more. So that's probably a good choice. If they happen to have 1 terabyte flash drives for $2,000 each, fill your bag with those.
2,000?
They used to be 10, but it came in a pen, so it was kind of worth it. Yeah, 1 terabyte drives are expensive.
Got mine for 300.
Oh, good.
Load up on.
I haven't looked in a while. Is it actually a terabyte?
1 terabyte Samsung Evo solid state drive.
No, flash drive.
Oh, the smaller?
Yeah.
Oh, I'd be skeptical of anything
Flash
that's
small.
small.
They make terabyte flash drives, but if you go on Amazon, most of them are actually terabit. So it's like 128 gig. You're like, wow, I got a terabyte drive for only $20.
Yeah, and it turns out it's just.
And it's only 128 gig.
Yeah.
So these things are little. They weigh like, a couple of ounces, and if they cost $2,000 each, obviously load your bag up with those, right? So the question is, how do we find an algorithm to maximally load the value of your bag? Did you find a flash drive?
Yeah, $3,424.
Oh, cool. Okay.
It's prime.
Nice.
Oh, wait, how big are we talking there?
A 1 terabyte flash drive,
Like-
and just the little tiny thumb drive.
USB stick? Oh, wow.
Yeah.
I would be
But
curious.
the 128 gigabytes are so cheap. It's like, just get 8 of those and tape them together.
Well, I mean, they have to be like, they're definitely smaller than a credit card size now, but.
Yeah.
That's crazy.
All right, so this is the general setup for a knapsack problem. And there's a few different ways to do this. So one version of this is called the fractional knapsack problem. And here, the competition is taking place like in a natural food store, where they have big bins of bulk produce, and you want to fill your 20-pound bag, but you can take as much of any item as you want. So here's some oats, and these cost $5 per pound. And here's some pumpkin seeds, and these cost $13 per pound. And here's saffron, and that costs, I don't know, $50,000 per pound, or something ridiculous like that. And so what's the best choice for filling your 20-pound bag? Go get 20 pounds of saffron, right? And that's going to be worth a whole lot more than 20 pounds of oats or 20 pounds of pumpkin seeds, even though pumpkin seeds are really good.
Assuming you can sell it.
Yeah, so eBay, someone will buy it. So it gets a little more interesting if you have limited inventory. So let's say they have 50 pounds of oats, and they have 10 pounds of pumpkin seeds, and they have 5 pounds of saffron. So yeah, this little corner store has $250,000 of saffron sitting in a bin.
Actually, how much saffron can cost, too.
Is it really? Okay, I know it's worth a lot. They haven't automated the picking of it. All right, so let's say that your bag has a capacity of 20 pounds. Right? Pretty clearly, you want as much saffron as you can possibly get. So you empty the saffron bin, you take all 5 pounds and you load that into your bag. Okay, so now you've got value and capacity, and here's what we add. So add 5 pounds of saffron, and that's worth $250,000. And now the capacity of your bag is only 15 pounds. and there's no more saffron left in the store.
That's why they only let stupid people win those.
Yeah. All right, so what should you buy next? What should you put in your bag next?
10 pounds pumpkins.
Right, obviously take as many pumpkin seeds as you can, and there's only 10 pounds, so 10 pumpkin seeds, and that's going to be worth $130, and that's going to leave you with a capacity of 5 pounds, and well, I guess I'll take the oats, because that's the only thing left. So we'll take 5 pounds of oats, and that's worth $25, and now your bag is totally full. Okay, that algorithm we just did is appropriately called a greedy algorithm. A greedy algorithm I think of as basically an algorithm that's trying to find the best solution at each point in the process. It's never looking ahead. It's saying, ooh, saffron, nice, give me that. And you fill up on saffron, you just keep taking it until it's empty, and then you go like, oh, no more saffron. Oh, pumpkin seeds, I'll take pumpkin seeds, right? And you're not looking at the price or the value or the capacities of any other item. You're just going for the most valuable item and loading it in. And that works for a fractional knapsack problem. It works because we can take any amount that we want. If there were only 4.5 pounds of saffron left, we can take 4.5 pounds and then 10 pounds of pumpkin seeds and then 5.5 pounds of oats. And we can prove pretty easily that this gives you the maximum value for a bag of given capacity. A greedy algorithm does not work, though, if we restrict you to an integer number of each item, if your items are indivisible. It gets more subtle. So let me see if this is a good example. These are always questionable. So here's an item. Here's its weight. No, I have to put this over here. Here's an item. Here's a weight. And here's a value. So item 1, I don't know, it's a mouse. And it weighs 7 pounds, ounces. It's a workout mouse. And it's worth $5. Item 2 is a drive, and that weighs 10 pounds, and it costs $9. One of the old 10 kilobyte drives. Item 3 is a phone. It also weighs 10 pounds, and it's worth $9. And item 4 is a laptop. And it weighs 24 pounds, and it costs $12. These are weird examples, right? All right, so suppose your capacity of your bag is 25 pounds. If you calculate value per pound, this is 0.9, this is 0.9, this is 0.7, and this is 0.5. So what's our best way to stuff things into this bag? And I never know if the solution, the example I come up with is a good one or not. And this is from notes that are a year old. But is it clear what the best solution here is? The most valuable item is the mouse. So we might try to load up, sorry, the most valuable item is the drive. So we might try to load up on drives. So 2 drives. So here's item, here's value, here's remaining capacity. So if we take 2 drives, that's worth 18, and that weighs 20 pounds, so it leaves us with 5 pounds in our bag. And there are no 5-pound items, so that's all we can get is 2 drives for a value of 18. And yes, this is a bad example because that turns out to be the best thing to do.
No, it's not.
You get a drive in 2 months.
Or a phone in 2 months, yeah. You end
Uh,
up with 19.
Yes, okay, good. So, so if we get a drive plus 2 mice, 2 mouses. All right, so that's 10, and 14 will be 24. That'll leave me a capacity of 1, but that'll give me a value of 9 plus 10 is 19. So we get a higher value in our bag by not picking the most valuable item first, which can seem counterintuitive. But you can see what's happening by picking the most valuable item first. We ended up with 5 pounds of capacity in our bag that we could not use. By picking less valuable items, we were able to use more of our capacity. We ended up with 1 pound unused. So a greedy algorithm won't work when we're constrained to not being able to divide these and take a fractional part of a laptop, for example. All right, so let's take a 5-minute break, and then we'll come back and we'll look at a recursive algorithm for tackling this, and then we'll apply that algorithm to another similar situation, which is a rod cutting problem. And this is probably going to be your final programming assignment. We'll be doing a knapsack problem recursively with and without dynamic programming. So we'll come back and we'll talk about details of that.